Hello, I'm Haiyan Wang, and I'm excited to talk about our latest research, Rethinking the Learning Paradigm of Dynamic Facial Expression Recognition. In a nutshell, we came up with a weakly supervised approach to model DFER as a multi-instance learning problem. We also noticed that there's an imbalance between short and long-term temporal relationships. This makes it tough to model the entire temporal relationship or use time-irrelevant methods. Our proposed framework provides a unified solution to the weakly supervised problem and models the imbalanced short and long-term temporal relationships in DFER. To top it off, our method achieves state-of-the-art results compared to other methods, even when using a vanilla R3D18 backbone. Plus, we did some cool visualization experiments to analyze our method's performance and uncover unsolved problems. Let's dive into the details. Facial expressions are crucial in communication. Being able to understand someone's emotions through their facial expressions is super important during conversations. That's why automated recognition of facial expressions is a big deal in fields like human-computer interaction, mental health diagnosis, driver fatigue monitoring, and even meta-human technologies. But here's the thing. Sometimes it's hard to tell what someone is feeling just from some frames. For example, we might classify an expression as neutral from these frames, but then classify it as angry from the next frames in the same video. Previous research has considered these non-target frames as noisy, but we propose that it should be treated as a weakly supervised problem where the labels may not be exact. Additionally, we found that there is an imbalance of short and long-term temporal relationships in DFER. Short-term temporal relationships show complicated facial movements, while long-term temporal relationships show smoother emotional changes. To tackle these challenges, we followed the multi-instance learning pipeline, which involves 4 steps: instance generation, instance feature extraction, instance aggregation, and classification. We use 3D CNNs to extract features from the 3D instances and learn the strong short-term temporal relationship. We also use a dynamic long-term instance aggregation module to model the long-term temporal relationship while dynamically fusing the instances into the bag. And to keep things consistent on both the bag level and instance level, we introduced the dynamic multi-instance normalization. Now let's talk about the experiments. We compare our method with the state-of-the-art methods on 2 in-the-wild datasets DFEW and FERV39K, and the proposed framework outperforms these methods with vanilla R3D model as backbone. We also conducted some visualization experiments to analyze the performance and uncover unsolved problems. For example, we looked at how our method performs on a single instance in a sample with strong facial movements. We found that traditional 2D instance-based MIL is heavily influenced by the facial movements when the subject is talking. But our framework can recognize confusing expressions with confidence given by these instances and successfully predict the emotional status of these tricky samples. From the confusion matrix and the TSNE visualization, we observed that the model struggles to predict the emotion of videos labeled as disgust or fear. This is due to the severe label imbalance in DFEW, where the proportion of disgust videos is only 1.22 and fear only has a proportion of 8.14. Additionally, we observed that the model tends to predict the label neutral more frequently. This is because some expressions in DFER have much lower intensity than static expressions. In conclusion, we conduct a thorough analysis of the DFER problem and propose a new learning paradigm. We utilize the multi-instance learning pipeline and develop the M3 DFER framework to address the weakly supervised problem and imbalance short and long-term temporal relationships in a unified manner. Our extensive experiments support our perspective on the DFER problem and demonstrated the effectiveness of the proposed framework. In addition, we have identified several research directions that may guide future studies in this field, such as the imbalance label problem, the uncertainty problem, and others.